This is Radio TV Phono Nut, and here's something that I don't know what it is as of yet, so let's try to figure this out together. So we have a box here with a handle on it and what appears to be a speaker on the front and two knobs on the front. One of them is obviously a potentiometer with no click, so no switch on that shaft, and this one over here is obviously a switch, probably the power switch. On the back here you can see we have a rear cover that's screwed in place at the bottom and has a snap thing on it to where the cover can flip down. So let's see what we got here. So we have a speaker and a rotten power cord. So let's go get a screwdriver and open this thing up and see what we have on the inside. Is this an amplifier? Is this some kind of fixed frequency radio receiver, or what is it? Here we are with the back cover removed and a power cord that has melted and stuck to the chassis. 110 volt 60 cycle AC model OP, and it looks like we have the standard patent label notice that's attached to the back of radio receivers, which would suggest that this is some kind of radio receiver, but it could also be a generic label that got stuck on everything just to cover their butts. Alright, so let's see what we have here. It looks like we have a power transformer, 3 tubes, something in this box, and some kind of box back here, probably a filter condenser. So what kind of tubes do we have here? Alright, this is a type 80, so that's obviously a rectifier tube. We'll set that to the side. This is probably an audio output tube of some description. A 6B5, yeah, that's an audio output tube. And then we have another tube back here that's shielded. And in order to more easily remove that other tube, I'm going to have to take the chassis out, which is something we need to do anyway, so we might as well go ahead and do it now. And the other tube is a 6C6. Looking under the chassis, I see nothing but a bunch of capacitors or resistors, no coils anywhere, which pretty much rules out the fact that this is a radio receiver. And there's some kind of transformer inside of this, probably a audio matching transformer. Alright, we have 3 wires here. One connects to chassis, which would be your shield, and then the other 2 are our signal inputs. And we see 3 holes in this little cover that snaps into place. So I suspect this probably connected to a cable that had some kind of jack on the end of it. So this is probably either a portable PA amplifier or a portable instrument amplifier. Of what type, I don't know yet. And as far as this model OP, that's the only identifying mark I can find on this thing. Well, I found out what we have is a Simplex model OP public address amplifier that originally had a hardwired microphone to it, and the plane is going to fly over just as I'm getting ready to talk. And how I found that out is I looked up the 6B5 tube, since that's a rather oddball tube, and by the way, that's a dual triode that's direct coupled. One section I believe is a driver and the other section is the power output stage, but I looked up a type 6B5 tube since that's a bit of an oddball one and would be less items to have to search through. And we got to the Radio Museum website, and they show you all of the model entries by year of what they have on file that uses this tube. So I got to 1936 and went through all the listings, and it gives you the make and model of the item, and then it tells you how many tubes it uses. And I found a model that said it used 3 tubes, and it listed the brand as a Simplex model OP, which is in Riders Volume 7, which we will consult if we end up needing a schematic. And that's indeed what this is. This is our microphone connects here to the primary side of this audio matching transformer, and then the secondary side connects to this driver tube, which in turn connects to this audio output tube, and then the rectifier provides our DC voltage for the whole thing. So this thing, assuming the transformers and the field coil are good, and an ohm meter check should prove that, this should be an easy restoration. Just a recap and changing any out of spec resistors and cleaning the controls, and it ought to work fine. Now, as far as an input, I could drill a hole on the cabinet and put a 1/4 inch jack, but I really don't want to molest this thing because this is probably a very rare unit, and me drilling a hole in the cabinet to put a jack would only devalue it. So at best I might add some kind of cable here that has a female jack on it where we can plug a microphone or whatever into it. This could probably also be used for an instrument amplifier, but you know, we'll probably just use it as a small PA amp. Alright, checking the transformer, the input transformer. This is the ground, which I believe the transformer has a center tap that is connected to ground. So let's see if this is any good. When the meter decides what it wants to settle on. Well, we're going to say 105 ohms. And about the same for that side. So that is good. And just reading directly across the winding. Well, maybe that center tap doesn't connect to ground. I'll have to consult the schematic one more time, but yeah, as far as I'm concerned, that transformer is good, or the primary is good. It has continuity. Here's the secondary. One lead goes into the volume control, the other lead connects to chassis, which is ground. Bottom of the volume control connects to chassis. The output of the volume control goes into the control grid of the 6C6 tube, and we're reading 2.6K, so that's probably about right. Checking the speaker, this is probably the field coil, 2.3K. That's, you know, field coil can be anywhere from 400 ohms up, or well, 250 ohms is about the lowest I think I've seen, up to a few thousand ohms. This one's towards the high side, 2.3K. Now let's check the primary of the output transformer. Alright, 411 ohms, that seems about right. Now the secondary and the voice coil, we really won't be able to check that unless we disconnect the secondary winding from the output transformer from the voice coil. Or I could place a voltage across this field coil and connect a 9-volt battery across the primary, and if everything is okay, we should hear a click in the speaker. But I'm just going to go ahead and assume that the secondary winding of this transformer and the voice coil are both in good shape. I hope I'm not making a mistake by assuming. You know what often happens when we assume, make an ass out of you and me. Next, I think we'll go to the workbench, put a power cord on this, remove the 80 rectifier, and make sure our power transformer is healthy. That's something you really can't, I mean, you can do a continuity test on a power transformer, and sometimes that'll be revealing, but sometimes it won't. Usually the best way to check a power transformer is to bring it up under controlled conditions, as in through a variac and a dim bulb tester with no load on it, and see what kind of voltages you get on the secondary windings, and see how the dim bulb tester acts. If the bulb glows brightly, then you probably have a shorted power transformer. If it glows dimly, then you're probably in the clear. So here's what we have. We have a polarized power cord. Black will be the hot, white will be neutral. And the way it looks like they have this wired, one side of the line goes up to the power switch. The output of the power switch comes down to the one wire on the primary winding of the power transformer. And then our other side of the line connects to directly to the other lead of the primary winding on the power transformer. And then we have a noise suppression capacitor connected between also that side of the line and chassis. So that capacitor will eventually be replaced with a safety capacitor. We'll connect our hot side of the line to the switch, and our neutral will go here to this other lead going to the power transformer primary and the chassis RF noise suppression cap. Power cord replaced, chassis isolation cap, or in this case RF suppression cap, replaced, and I had to relocate it because of the short leads on here. We have the amplifier plugged into the dim bulb tester, which is a 60 watt incandescent bulb, and is also the only size I have at the moment. And then we have the dim bulb tester plugged into the AC power supply, and we have our AC voltmeter connected across the high voltage winding on the power transformer. And we're now gonna crank this thing up and see what we get. And we're getting voltage. That's a good sign. 45 volts at just very little AC input. That's an excellent sign. Now we have 115 volts AC at about 15 volts AC input, so that's good. So we're just going to crank this thing up. This is probably a 700 volt center tapped winding, and given the output voltage that I have with maybe 50 volts AC input, that sounds about right. Well, yeah, about 700 volts, but that transformer's humming like a... Well, it shut up then whenever I put my hand on it. Maybe I need to try tightening down the bolts. Maybe that'll put a permanent stop to it. But yeah, 694 volts, so that's... And it would be 700 volts if I didn't have the bulb connected in series with it. Well, we're up to 700 now. And the bulb is basically not glowing at all. Now we're going to check from one side of the high voltage winding to the center tap, and then the other side of the high voltage winding to the center tap, and we should have approximately the same voltage on both ends from each end of the center tap. Alright, 349 there, and 350 there. So yep, that's 349, 350. So yep, the high voltage winding appears to be healthy. Now let's check our 5 volts on the rectifier tube heater, and then we'll check for 6.3 volts on the heater pins of the other tubes. Alright, 5.3 volts, that's good. And remember, we still have the bulb in series, so that's going to affect it a bit. Yeah, we're going to have to do something to try to quieten this transformer down. And the 6.3 volt winding under load, because I did not remove the tubes, is reading 6.7, so that's healthy. So electrically this transformer seems to be in good shape. We have the proper voltages coming out of it. We do not have excessive bulb illumination, and we do not have excessive current draw here. So all we really need to do to this transformer is tighten everything down and try to quieten it down, and it should be okay. Alright, we have the speaker connected, which by the way is in nice shape and has no voice coil drag. This amplifier was obviously kept in a indoors in a decent location all of its life, because it's held up too well just to have been stored in a barn or a shed or some place like that for the past 70 plus years. But anyway, we had the speaker connected, the rectifier tube reinserted, and we're plugged back into the dim bulb tester. We're going to bring it up slowly again and see what happens. See if we produce any DC B plus voltage at the cathode of the rectifier, and then we'll go from there. Yeah, starting to see a little something there, but it's going to take a few minutes. I'll kill the camera while this warms up. I won't bore you with waiting on this to warm up. Alright, we were getting no B plus to amount to anything. And whenever I check between the cathode of the rectifier and chassis, we see 0 ohms here, which of course is a short. That's the reason we bring these things up very slowly and very carefully, so we can catch things like that before they cause damage. I unplugged the speaker and the short is still present, so whatever it is on the input side of the speaker field coil, likely a shorted filter capacitor, or if there's a bypass capacitor from B plus to chassis, then that could also be bad. Alright, looking here at the cathode of the rectifier, we have one lead that runs off into this filter condenser block, and then we have another lead that runs over here to the speaker field coil, or speaker plug, which happens to be the field coil pins. Okay, so we unplug the field coil and the short is still present, and there appears to be nothing else soldered to that terminal, so that suggests that this filter condenser block is shorted. And as we can see, the short is still present. Just for fun, I'm reading across the other section of the filter capacitor, and it's slowly rising. So that capacitor is very well, that section's no good either, because if this was a good healthy electrolytic, which we know one after almost 90 years likely isn't going to be, it would basically just blink and go away. I've disconnected that section of the electrolytic from the rectifier tube, and as you can tell, the short is still present, so that capacitor section is indeed no good. Alright, just to clear up some confusion here, I was reading 0 ohms from the cathode of the rectifier to ground here, and there's nothing else there on the cathode of the rectifier except the input of this speaker field coil here, which also serves as a filter choke. Now, technically, had the short been on the other side of the speaker field coil, even if we shorted this output of the speaker field coil directly to the chassis, and if I read from the cathode of the rectifier to chassis, I should have still read around 22,000 something ohms, the resistance of this field coil. But I have learned in the past to always cover your bases, no matter how slight the possibility of something going haywire. Always cover yourself. So to cover myself, I just went ahead and unplugged this just to be sure. I mean, in this case, the speaker frame is not connected to ground in any way, but in some cases it is connected to ground, and if there was a short in this field coil that was shorting the field coil to the frame of the speaker, then yeah, that would produce a low ohm resistance reading from the cathode of the rectifier to ground. But I remember years ago a fella I know, he was more of a solid state guy. Somebody brought him an old guitar amp. I don't even remember the brand, but it was from the late 40s, early 50s. And the complaint was it was blowing rectifier tubes as fast as they stuck them in there. And that's why you shouldn't do that. Rectifier tubes generally don't just blow up on their own. So this guy replaced the filter capacitors, and it still didn't correct the problem, so he was lost. And at that point he brought it to me and let me have a crack at it. And sure enough, there was a dead short from the B plus line to the chassis, which was B minus or circuit ground. Well, come to find out what the problem was, the audio output transformer's primary winding was shorted to the core of the transformer, and since the transformer was bolted to the chassis, then that provided a direct short path to ground there. So I replaced the audio output transformer, and the amplifier came to life, and everybody was happy. So just don't ever assume that something can't happen. And in another radio repair that I did a while back, we had some B plus on the plate of the output tube, but not nearly enough. It was like 112 when it should have been like 140. And it turned out to be the primary winding of the output transformer in that case too. Reading across it with an ohm meter, I read wide open, but for some reason it was passing some voltage through whenever it was hit with juice. The only thing I can come up with was the transformer burned up and arced, and maybe there was some carbon tracking inside that provided a high resistance path to give us some B plus voltage, but yet read wide open on an ohm meter. Alright, enough babbling about that. The schematic calls for two 8 microfarad 450 volt caps. Well, we can use 10s, and that'll be just fine. I've soldered a terminal strip right here to the chassis, and the new capacitors will be very small, so we can put those right here, and they won't be in the way of anything we need to troubleshoot, hopefully, and then run wires from the terminal strip to the correct places in the circuit, and then we'll be good to go. Alright, here's our new two 10 microfarad capacitors. Negatives tied to the chassis here, the banded end of the capacitor, since chassis is B minus. Then our positives here, and I just simply snipped off the lead from the old filter block and ran it up here to this terminal, and then we used the old lead from the other section on this terminal. Now we'll reapply power, and I think things will be a lot happier now. Now, first filter capacitor off of the cathode of the rectifier. Watch the meter as I touch it to there. See, it went to 0 and then went to 20 megs, 19 megs. That's what it's supposed to do. Now, second filter capacitor. Basically the same thing. So that's what we want. I bet you that short circuit is probably what put this thing out of commission in the first place. Now let's just hope the 80 rectifier isn't cremated, but if it is, that's cheaper than a new power transformer. And it's also situations like this where it's probably a good thing the power cords are too dry rotted and crumbling for someone to plug in. Although I have seen people do it stupidly, but they still do it. But yeah, for the most part, people see a crumbling power cord and they shy away from plugging something in, so that's probably a good thing. Alright, let's give it some juice and see what happens. Oh yeah, 280 something volts B plus so far. And we're only at about 60 volts AC input. So we'll let it warm up and see if we get any kind of activity. $235 volts, 200. So obviously the tubes are starting to conduct. Alright, I'm not hearing any buzz at all in the speaker. So that tells us that most likely the audio output stage isn't working. Well, when I touch the top cap of the first audio tube, I get a little tick in the speaker, but not much. Crank the AC input up a little bit. Yep, we're hearing a very light hum here. I believe this is the plate of the first audio tube, and we have 188 volts. Now we go through this coupling capacitor here, over here. What do we have here? 179 volts. Well, that would suggest that that capacitor is big time leaky. Actually, I think this little capacitor is the plate to grid coupling cap between the first audio and the output tube. So let's check on the control grid there on the output tube and see what we have. We have 98, 99, 100 volts. So yeah, I think we better kill that. I don't want to cremate this 6B5 tube. I doubt I have one, and it's probably not a cheap tube. Alright, I have the grid end of that coupling cap disconnected. We're just going to see what kind of DC is on it with it unloaded. And as far as that shorted filter capacitor, we rarely ever run into an electrolytic that's actually shorted to the point that it reads 0 ohms when tested across an ohm meter. But it does happen from time to time. Usually they won't check dead shorted on an ohm meter, but whenever high voltage hits them, then they'll leak so badly that, you know, they might as well be a short. Alright, let's apply power and see what we got here. Oh yeah, that capacitor is extremely bad. See, there should be no DC there at all, but we're reading 139 volts and rising on that grid side. So that capacitor is very, 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 very bad. As far as resistance goes, we're reading about 226, 830K and rising. We'll see where it tops out at, but it's not going to get much higher than this. So this is more like we'll just say a 270K resistor is more like what this capacitor is the equivalent of. Alright, after a couple of minutes, it's almost 400K. That's because this capacitor is so leaky that it's taking an extremely long time to charge. That was me touching my leads together down here. Or what's going on here? Something trying to come loose? Actually, this capacitor is now causing my ohm meter to do weird things. No, actually what should happen, for a brand new capacitor, I should touch my meter leads to it and it should just go blip and then go to an overrange condition. This is a Ducko brand. Never heard of that. But anyway, it's a 0.02. 0.02 at 600 volts. Here's a new 0.02 microfarad capacitor, and I'm going to show you how this will do on an ohm meter. And this is a brand new capacitor. Let's see if I can do all this one-handed. Oh, I touch the meter lead with the other hand. See, it don't even, it's so quick, it doesn't even, the meter doesn't even have time to react to it. So that's what a new capacitor should read. Now, my mentor that was a retired radio and TV repair technician from back in the old days that I met in the early 1990s, that taught me a good bit of what I know about radio. And he wasn't one to just go in and replace all the caps right out of the gate. In fact, he made fun of those people who do. What he used to fix a radio for the most part was his vacuum tube voltmeter and his big Weller soldering gun. That was it. And the way he checked a capacitor is with the resistance range on his vacuum tube voltmeter, like the 1 meg range on his meter, or 10 meg range, whatever the highest scale was on it. And if he saw the needle flip towards 0 and then rise back up, then he knew he had a good capacitor. If the needle went down towards 0 and didn't rise very high, then he knew he had a capacitor that was too leaky to leave in circuit. Now, this guy was also very tight when it came to his money. He was one of those that grew up during the Great Depression, and he knew how it was to be financially embarrassed. So he rarely ever ordered capacitors. When he'd change a capacitor, it was usually one out of his junk box, something that he'd cut out of an old television or something like that, because he was all the time picking up old tube type TVs and radios and stereos that was in bad shape, and ones that had decent components in them. He'd whack them out and throw them in his paint can, and whenever he needed a capacitor, he'd just go to his paint can. And in the case of an amplifier here, we're going to try to identify the outside foil of the new capacitor. It probably won't make one iota of difference. 99% of the time it doesn't. But seeing as how this is an amplifier, we're going to do it just to try to make sure we don't get any hum pickup here. So the way we do this, we have our oscilloscope clipped across it, and I'm squeezing very tightly, and we count the number of divisions there, and then we'll reverse our leads and squeeze very tightly again and count our divisions, and whichever end gives us the greatest amplitude on the scope, then whichever terminal on the capacitor that the plus lead is clipped to, then that will indicate our outside foil end. So I'm squeezing real tight. Now, you know, they say don't squeeze the Charmin, but it's okay to squeeze the capacitor. So we have 1, 2, 3, about a little over 4 divisions there, if I'm seeing this well enough. And on that side we've got about a little less than what we had, a little less than 4 looks like. So the terminal with the red clip on it is the outside foil, and that will connect to the lowest impedance point in the circuit. In this case, it will be the plate of the first audio tube. So our foil side is the right hand lead of the capacitor, but don't assume that it'll be that way on every capacitor. I might pull another 0.02 out of the drawer that's of this same brand, and the outside foil lead might be on the left hand lead of the capacitor. Now, since this other capacitor also connects to the plate of the first audio tube, I thought I'd go ahead and change it too. And these are so good that all you got to do is heat the capacitor, heat the tube socket terminal up to unsolder the lead, and it'll just, the whole end will just pull right out of the capacitor. So yeah, they use some very low quality parts in this, even for 1936. And this is taking a lot longer than I'd like, because about all I've got left of my desoldering braid is a bunch of soaked up sections, and I'm going through it trying to find portions of it that's not soaked as bad, that'll still take some solder, and then this desolder pump that's fairly useless. I've got some desoldering braid on order. It just hasn't gotten here yet, and it's times like this is when I miss the local parts house. We could just run down there and get what I need and come home. Now there's no parts house, so things like solder, desoldering braid, heat shrink, tubing, stuff like that, electrical tape, there's no place you can get it around here anymore. But there are plenty of liquor stores and Dollar Generals and cash for title places. There's plenty of those kind of businesses left, but no parts houses. And at one time there was about 4 of them. Let's see, there was Risher Radio Supply, there was Hooper Electronics, there was the Lafayette store, and there was Radio Shack. Lafayette store, I think they were before my time. They were gone probably by the late 70s, early 80s. Risher closed in the mid 80s and moved to Philadelphia, Mississippi. Hooper's hung on until sometime during COVID. When Mr. Hooper died, they closed down the parts house and combined it with the stereo and video store, and from that point on it was just really never the same. And then they eventually just shut the whole works down, and the old Hooper building is about to be home to a shoe factory. So there you go. And we can blame a lot of this on the fact that nobody repairs things anymore, and there's too many big box stores that people can go to and buy a new TV or whatever, and then whenever it breaks you just throw it away and buy a new one. I know Mr. Hooper told me before he died that when he opened his business in 1960, TV and radio repair was his bread and butter, but if he had to depend on that today, he'd have to close his doors. He said the commercial accounts, such as the schools and the hospitals, were the only places keeping him in business. So now I guess they're having to order stuff online too. Now my mentor, he'd get these things loose by just heating them up with his big soldering gun and yanking the hell out of these leads and getting them out that way. But I really don't like doing that because you don't know what kind of condition these sockets are in. You start yanking too much, you're going to break off a socket terminal. Been there and done that, and I don't like changing tube sockets. That's right up there with restringing dials in my book. So I try to be careful with them, and sometimes I've still ended up breaking off a tube socket terminal. Alright, I finally got everything off of that terminal, and while we have everything loose, we're going to meter these resistors. This is a 200K 20%, or excuse me, 10%. I assume that's a silver band unless that's just paint loss there. Alright, so what does it read? Body in dot. Red, black, and then our multiplier dot, which is yellow. And that reads, if the meter will get on there and stay, 245K. Well, that's out of the 10%. That's out of the 10% window there. Alright, we got this plate to grid coupling capacitor plate replaced, and this plate bypass capacitor for the first audio tube replaced, as well as the 2 resistors, one being the grid leak resistor for the audio output tube, and the other one being a plate load resistor for the first audio tube. And this is the way they had it done from the factory, so this wasn't exactly the neatest build anyway. That's the reason when we got to the other end of this plate bypass capacitor, I J-hooked it in place, because you see all the crap we got going here. And with me being out of desoldering braid, I just wasn't in the mood to deal with that, so there you go. Now we're fixing to run a test on it. I got a feeling it's going to do better this time. It might even pass a signal now. Alright, 309 volts and dropping as the tubes come into emission. Yeah, I touched the top cap of the first audio tube and it threw it into oscillation. Volume control's working. This top cap is not making very good connection, and I think we're going to have to address that. So right now is as good a time as any. Yeah, you can see this is about to come off, and we have little strandies sticking out that could very well be touching this tube shield. So yes, we need to go ahead and fix this. All right, we have that resoldered in place, so that problem's solved. All right, I'm still not getting much in the way of amplification, so I had the plate bypass cap for the output tube loose. One end connects to the actual plate of the tube, the other end connects to B+. So either end I disconnect, there's going to be DC on the other end. So I want to see if there's voltage right here on the loose end. So let's turn it on and see. And yeah, there is 380 volts. .328 volts as the tubes warm up. Yeah, that capacitor's cream puff too. And this capacitor is also, I'll get back on there. Gummits, get on there and stay. Give me a clip lead. Alright, that one's not dead shorted, but it's very leaky. We're up to like 900 k ohms across it. Alright, 2 is the plate for the output tube, 351 there. 3 is the plate for the driver tube, 354 there. 4 is the control grid for the driver tube. 227 there. What the heck? Something's not right there. And 5 is the cathode of the output tube, and I got 250. What the heck's going on here? Something is jacked up here. Is this tube shorted or what? Alright, I've got the tube pulled and I'm running this on reduced voltage. Alright, control grid, 57 volts. Cathode, which is where the other end of this 220k resistor connects, 59 volts. So something's wrong right in here. We need to see where this cathode goes off to. Alright, the cathode of the output tube, which is actually in this case the cathode of the driver portion of the tube, comes over here to this terminal, which also connects to one end of this capacitor, and then the other end of this capacitor connects to guess where. Looks like B+. When you want to bet this capacitor's shorted or severely leaky. Alright, let's see. I have these capacitors disconnected. And now we're down to like 3 volts on the cathode. Do we have B+? Yes, we do. 255. Alright, what do we have at the end of these capacitors here that we cut loose? 154 volts. So I think that's your problem right there. One or both of these capacitors are extremely leaky. Alright, I pulled those capacitors loose. And now we got oscillation and crap going on. But we still have our high voltage on the control grid and cathode of this driver section of the output tube. And when I remove the tube, I get a little positive voltage at those places, but not like what I was getting. But yeah, so that would suggest that this tube is shorted internally. And I'm hearing something popping as this thing cools down, like this driver tube might have gotten extremely hot. Or is it the rectifier tube that's doing it? Well, it don't matter, but I think I've had about all I can stand of this for today. Tomorrow we'll come back down and replace these capacitors. I know you're probably hollering, why didn't you just replace all the capacitors before you plugged it in? Well, normally I don't like just doing things that way. You don't really learn much that way, but maybe in this case, maybe I should have. Okay, here's the schematic as seen in Riders Volume 7. We have our audio coming into the primary winding on the input transformer, and then the center tap of that primary winding comes down here to a 150 ohm resistor and the plus end of a 50 microfarad electrolytic capacitor, with the other end of those two items connected to B minus. And then also connected to the center tap of this primary, we go to a, looks like a 100k ohm resistor. Bottom of that resistor connects to the bottom end of the secondary on that transformer. The volume control bottom end also connects to that point. And then the wiper of the volume control connects to the control grid of the 6C6, that's the top cap. And then the top end of that transformer, of course, connects to the high side of the volume control. And then we have these 0.5 microfarad bypass capacitors here. So yeah, you kind of get the idea of what's going on here. There's really not a whole lot to this thing. Alright, so let's get back down to the bench and start changing those other capacitors. I think we can just safely go ahead and replace those. They're all going to be extremely leaky anyway, so might as well not fool around with them. We know for definite that the audio output transformer and speaker are okay, and this input transformer appears to be okay, so there's really not much else to this. If you'll notice all the corrosion on these capacitor leads. So yeah, I think those need to go. Makes me wonder if something didn't piss in this thing at some point in time that caused that kind of corrosion, or maybe something was spilt in it at some time. I don't see any other evidence of it. Or it could have been just a case of atmospheric conditions just reacting with these leads on here, and they just corroded up, and that was that. Having to consult the riders again because we have two capacitors that are connected to the cathode of the first audio tube that we do not know the value of because the ink is faded. So we have a 0.5 and then we have a 5 microfarad, and that 5 microfarad is an electrolytic, and the reason I know that is because one end is red and the other end is black. Then we have a resistor in parallel with that electrolytic. It reads over 4K, but the paint on the resistor is faded and really can't tell much from that anymore. So that's when we consult the riders, and this looks like a 3K. Now notice it says 3M. No, that's no relationship to 3M that makes Scotch tape and the old woolen sack tape recorders. And it does not mean 3 megohms either. And a lot of old radio schematics an M behind the number usually means kiloohms. When they meant megohms, they'd usually just spell out MEG, 3 meg, not 3M. And that's where a lot of newbies make their mistake. They see 3M and they'll put like a 3.3 meg resistor in the circuit when it should have a 3K resistor. And then of course the circuit's probably not going to work correctly with that higher value resistor in it. Here's the resistor we're talking about, and I'll show you how to read these. You read them from left to right, and you see the block to the right has an arrow shape on it, and that shows you that. Looking at this, it would appear to be red, black, black. Well, I think it's supposed to be orange, black, red, but over time the paint is faded or flaked off or whatever. So that's why the writer schematics come in handy. And like this capacitor, it has no microfarad value left on it anymore. And like I said, this end's black, this end's red. The red end goes towards the cathode. So we need to replace that. And we need to replace this 0.5 microfarad here. And yes, I am going to clean this up. That's very unbecoming to me. I don't know what I was thinking. Just need to look at this from the standpoint that it hasn't worked in 70 years. It can wait a little while longer, even if I have to wait a few days to get my desoldering braid and clean this mess up and do it correctly. Well, either the schematic is wrong or this thing was wired wrong to begin with. The way it was wired originally, they had a 5 microfarad electrolytic in parallel with a 3K ohm resistor connected to the cathode of the 6C6 and connected over here to this lug, which goes to the volume control. And then they had a 0.5 microfarad capacitor also connected to the cathode of the 6C6. And the other end of the capacitor is going to the center tap on the primary of the audio output transformer. But on the schematic, they had the 5 microfarad going between the tube cathode, that and the resistor that's in parallel with the 5 microfarad, going down here to the center tap of the transformer. And that's also where the 50 microfarad capacitor connects. And then they have the 0.5 microfarad capacitor connected to the bottom of the volume control here. Well, I'm going to connect it like the schematic says. I mean, both scenarios are common. It's common for the schematics to be wrong. It's common for the chassis to be wired wrong. I've seen both instances, but I'm going to wire it the way I think it ought to be wired, and the schematic looks more justifiable to me. Alright, we've cleaned up my mess. Got everything off this terminal here. And what I might also do, if you recall from the factory, they had these two resistors joined together like this, and they were out of tolerance, so I changed them. I don't really like that. What I might end up doing is soldering a terminal lug right here on the chassis, and then we will run the resistors to the terminal lug, and then connect the capacitor to said terminal lug, and that will be a more stable connection than having all this crap flipping and flopping around in mid-air like that. Well, then whenever I remove the 0.5 capacitor from this lug right here, the original capacitor, it came off like somebody had probably put it there, so that might have very well not been a factory screw up. That might have been somebody else messing with this thing and screwed it up. And I can see how it'd be easy to do when you have one that's a 5 microfarad and the other one that's a 0.5 microfarad. Then yeah, it could be really easy to get the two transposed and connect them to the wrong terminals. Something else I noticed, we have a 100 picofarad capacitor that connects from the plate of the first audio tube, goes back to the center tap of the primary of the input transformer. Well, there was also this capacitor here that was there, and I just went ahead and replaced it because, you know, it was there and I guess I wasn't paying attention, but it was in parallel with this 100 picofarad capacitor, and I'm not seeing anything on the schematic that suggests that that's supposed to be there, so we're going to get it out for right now. Alright, we have everything in place, and I'll go back over my work one more time and make sure I didn't mess up anything. But don't you think having a terminal lug here is much better than having stuff just flapping in the wind? And that's the way they had it from the factory. Alright, I sort of suspicion this tube might be internally shorted. So what I've done, since my tube tester that will test these types of tubes is sort of buried right now, and this is not a conclusive, 100% conclusive test, but I have heated the tube up with my bench power supply set to 6.3 volts, and I've taken my meter here and I've measured between the elements of the tubes to see if there's any leakage, and there's not any, but of course there could be leakage that amounts to more than what my meter is capable of reading, but at least I do feel a little better about putting this back in there. And that's what I'm fixing to do. We're fixing to plug it back in, connect the speaker, and see if it blows up. Okay, we're powered up, and once again we're on the dim bulb tester and starting out at a very low voltage. Just in case something goes haywire, then we'll be able to have some protection here. Alright, at about 30 volts AC input, we have 49 volts B plus at the first filter capacitor, and that's pretty impressive for such a low input. It's amazing that the rectifier is even conducting at such a low input voltage, but it obviously is. Alright, looking at the control grid, that looks good. Of course, that might increase once we bring that input up and the set gets full power. Alright, 5 is the cathode, and we're not getting enough there to say we have anything. So let's increase the AC input to about 50 and see what happens. Got 182 B plus and rising. That's at the input filter. Okay. We're at 60 volts input. I am getting a little buzz whenever I touch the control grid of the audio output, or excuse me, the first audio tube. Well, when I touch any one of the input leads on the transformer, I get a little buzz from the speaker. So we're making progress here. Alright, I'm at full line voltage now, and we're getting 4.3 volts on the cathode of the output tube. I think that's probably a little low. I might just bypass our bulb and see if that has any effect on it. Well, that's pretty stout at the control grid of the first audio tube. Alright, bulb is bypassed. We have about 258 volts B plus. Cathode voltage is reading about 6. That's probably about what I would expect with a 150 ohm resistor. Alright, control grid voltage. Got about 6 volts positive there, so that leads me to believe that that output tube is most likely gassy. And I'm really not surprised by that, because that output tube was under a lot of strain with those bad components in there, so we're probably going to have to hunt us up another 6B5 somewhere. And I'm going to let this cool for about a half an hour, and then we're going to fire it back up again with our voltmeter clipped on the control grid And if it's a gassy tube, what will likely happen is it will first come up normal, and as it heats up, our voltage will swing more positive. And if it does that, then that'll be pretty indicative of a gassy audio output tube. Alright, we're clipped to the control grid of the audio output tube. We're going to power this up at full line voltage with no light bulb and see what we get on the control grid here. And it's rising up immediately. Alright, 6.7, 6.8 volts. And when I turn the volume all the way down, the hum goes away. So that definitely sounds like an open input there. So it's definitely working to some degree there. Well, this could be the reason. We have our grid leak resistor that connects between the control grid of the 6B5 and the cathode of said tube. And there's going to be a little DC voltage on the cathode, so it makes me feel a little better anyway. Well, dummy me, I had my meter clipped to the cathode the whole time, but anyway, we have 5.9 on the control grid. But I'm still going to let it cool off a few minutes and turn it back on and see what happens. See if we get any change in voltage. We shouldn't there, or not enough to amount to anything from the first turn on until after it's been on for a few minutes. So apparently what was wrong with this thing was a combination of somebody's miswiring that I followed in their footsteps without consulting the schematic first, which is what I should have done, and leaky condensers. And of course there were a few out of tolerance resistors too, but none of which were out of tolerance enough that it would have thrown the thing completely out of operation. I went ahead and changed them anyway, since I had to take them loose to get to these capacitors. But I think now we need to verify this output tube, and then we need to come up with a suitable vintage microphone like what was supposed to be used with this and give it a whirl. Now, of course, something like this is not suitable for a large auditorium, but for a small room, something like this would be okay. And you might be surprised how loud this would get with just 2 or 3 watts of audio output power driving a high efficiency speaker. It would probably get plenty loud enough for a small area. And I suspect this chassis was also used for a radio model, because if you look at these holes here below where the input transformer is, you can see they're punched and drilled here for 2 tube sockets. Yeah, most likely at one time most likely this chassis was also used with probably a little tabletop mantle style TRF set. And you can see on the front here where the speaker would have attached, you can see a hole there, and most likely the speaker had screw holes on the back where the magnet is to attach here on the chassis, where in this case they have a filter can. So yeah, and the control spacing on here looks just like what you would see on those little midget mantle style TRF curtain burners type sets from the mid-30s. So yep, multi-purpose chassis use here. Alright, I think this thing's had time to cool down. We're going to test it again, and this time I have the meter clipped to the control grid, but since that the other end of that grid leak resistor connects to the cathode, then yeah, it stands to reason that I'm going to see some positive voltage there with respect to circuit ground here. So let's hit the juice. And as you can tell, we've come to life here. But I think for all intents and purposes, this amplifier is fixed unless I end up having to replace one of the tubes. But other than that, I just need to find an appropriate microphone to go with this, and it ought to be good to go. Alright, not the most ideal conditions here, but I have the 400 cycle audio output from my signal generator feeding straight into the volume control. When we have it all the way down, we get motor boating. But when we turn it up, as you can tell, it passes a signal. So it is working. All we need at this point is the proper type of microphone to mate up with this matching transformer, and we ought to be able to get the word out, so to speak. And I feel like this could be modified for instrument use if someone wanted to. Seems like all you need to do is get the transformer out of the circuit and go straight into the volume control, and there you go. You could run a more conventional signal source into this, but keeping things original, I'm going to leave it alone, and we'll try to come up with a suitable microphone and see what happens. Okay, we're now to the point where we determine what type of microphone to use for this. Up until this point, I really haven't given that much thought, to be honest with you. All I've been concerned with is getting this thing to amplify. Well, I looked at the Radio Museum website and I found an ad for this amplifier. I think it cost $37.95 whenever it was new back in roughly 1936. And it shows a picture of the amplifier sitting next to its microphone, and it's just a typical generic looking microphone. It looks like a desk mic, but it's small enough where it can be stored inside of the rear of the amplifier. And they mention in the ad that it is a carbon microphone, which, looking at this circuit, makes sense because a carbon microphone requires a small DC voltage in order to operate. Carbon microphones were used in telephones for many decades, but a carbon microphone is essentially just some carbon granules in between two pieces of metal, with the top piece of metal being a very thin diaphragm that vibrates with air pressure, and which changes the resistance of the microphone as the hold on. So as I was saying, we have a carbon particles between two metal pieces, with the top metal piece being a very thin diaphragm that vibrates with the air pressure applied to it from the human voice, which changes the resistance of the microphone. Now, the carbon microphone has a small DC voltage applied to it, and whenever you speak into the microphone, that vibrates the diaphragm, which compresses and decompresses the carbon particles, which changes the resistance, which thus modulates the DC voltage that's applied to the microphone. And that's basically how those work. Now, in this situation, we're getting our DC voltage for the microphone from the cathode of the audio output tube, and as you can see, it's applied to the center tap of the primary winding on the matching transformer here. And in this case, In this case, it looks like we have a dual element balanced microphone, since we have a center tap primary here. Now, what I've done for testing is I dug out an old telephone. It was actually the old rotary dial phone that was in my dad's workshop for umpteen years, and I removed the microphone out of it. We connected one side of the microphone to ground, and then we connected the other side of the microphone to one of the outer leads on the primary winding of the transformer, and it does work. So now all we have to do is find a proper microphone for this, and we ought to be in business. I feel like somebody whacked off the original microphone because they saw dollar signs. Whenever I was looking on eBay for microphones, I saw a bunch of old carbon microphones. I don't know if any of them were dual element types or not, but they were all way more expensive than what I think they should be. And I'm not going to spend an arm and a leg on a microphone for this. It's just not going to happen. So if anybody has any ideas as to how I might can solve this microphone problem, then I'd appreciate you speaking up. And if we can't find something, we may just end up bypassing this transformer. I'll leave it in circuit, but we'll just remove it from the circuit and put an audio input on the volume control and let it go at that. Alright, here's the old telephone that was in my dad's workshop for umpteen years. I'm covering up the phone number on it because that's still our current phone number, and I don't flash that number around everywhere. Actually, we've had the same phone number at this house since 1963 when my dad bought it. You know, you really can't find too many people left in today's world that can make that claim and that had the same phone number for close to 50 years. Actually, I believe they had that same phone number as far back as 1957 at the house they lived in before they bought this one. And I've hung on to it. We still have a landline. Probably one of the few in the neighborhood that still have a landline telephone, although I don't know how much longer that's going to last with the prices of landlines continuing to go up. If we do end up going with something else, I'll try to go with something where I can keep the same phone number. I'd hate to get rid of it after all these years, 60 years almost, doing the math. Alright, here's the carbon microphone out of the phone. I'm going to try to do this. I don't know how well I'm going to be able to do it with one hand. And this thing has a lot of gain to it with a microphone. I have the volume just barely cracked. If I turn it up any higher than that, we get feedback. So that tells me this thing is working. So let's turn it on, let it warm up, and see what we can do here. Testing, testing, 1, 2, 3, testing, testing, 1, 2, 3, 4. It seems to be working, and when I move the mic closer to the speaker, we get feedback. So I'd say this thing is repaired, except for finding a suitable microphone for it. Bell system property, not for sale. So that sort of updates this thing. But yeah, kids today would they would be blown away if they had to make phone calls using a rotary dial phone that's attached to the wall via a cord. Imagine the horror. But one thing about it, these old types of phones always work, unlike a lot of these cell phones that you can't get good reception on. And looking at this cover, it looks like this had some kind of plug on it at one time. You can see the two holes here where the rivets or bolts would have gone that held the plug in place. I'm not sure what kind of plug this would have been. I'm not really familiar with 1930s microphone plugs, but yeah, I think we're at a point now putting this back together, and if and when I find the proper microphone for this, then we'll do a part 2 of this thing, and then we ought to have us a nice little portable PA set up then. Alright, we're back together, and the power cord would of course be stored back in here, and I presume the mic would rest on these blocks here that the back cover screws into. That would prevent the mic from falling down and hitting the tubes or whatever. Now, I don't expect to find an exact type microphone like what came with this, but as long as I can find something suitable that will fit inside of the back of this set, then I'll be okay with that. Alright, here we go. So it's tabled until I can come up with a suitable microphone. And if any of you out there who are more proficient about vintage microphones than I am can recommend something that would work with this, a carbon dual element balanced microphone, preferably something that won't break the bank. I'm not looking for some $200 or $300 or $400 plus collectible microphone. I'm just looking for some generic old microphone that I can put with this and make it usable. So if you can think of something along those lines, then let me know, and the information will be greatly appreciated. Well, we're put back together for the time being, and when the time comes that I find a suitable microphone for this, you'll probably see a brief part 2 to this video. Here's the back side here. And as you can tell, the power cord stores in the back there, and the microphone would be a little desk type, but it would have to be small enough that it would fit in the back of the cabinet. And I presume the microphone would rest on these wooden blocks here that the back cover screws into. That would prevent the microphone from falling down inside the unit, and of course the speaker would also keep the microphone in place. Now, I'm not necessarily looking for the exact type of microphone that would have come with this originally. I know that may not be possible, but I would like to try to find a suitable vintage microphone that's small enough that would fit inside of this cabinet and have a dual element like what would have worked with this originally. And then once we get that, we'll have a nice little vintage PA system here. But from the ones I've seen on eBay, they were very expensive. Now, I didn't look at any of the carbon microphones on eBay enough to know if they were dual element or not. I just couldn't get past the prices. Well, we don't need any kind of exotic collector microphone for this. If I can find something for a reasonable price, then we'll go with it. If I can't, I'll just disconnect the transformer and we'll just use this amplifier as a more conventional amplifier and feed a signal of my choosing straight into the volume control. Alright, that's about all I've got for this video. I'm going to have some more videos coming in the near future, stuff that I've done and just haven't had a chance to edit it all together and upload it yet because of other things going on. But I need to do that soon because the memory on my hard drive is about full, and I need to get some of those videos together and get them out there so I can get them off my hard drive. I will tell you in advance, there's going to be a couple of them where I got carried away. I mean really carried away, and they got really lengthy. And when I say lengthy, I'm talking about mini-series lengthy. And I'll have to try to be careful and watch that in the future. If it's something that's going to turn into several hours, then I'll have to remember to try to do it in parts, and that way you won't be bogged down with a 3 or 4 hour video. Alright, there you go. This is about all I have for the little Simplex amplifier for now. Like I said, if anybody has any suggestions on a microphone, something that I might could use, then I'd love to hear from you. And when we come up with such a microphone, then I'll make a video of us putting it all together and giving this thing a test run.